This is an SD card. We've talked about it in the previous video at length. For today, all we really care about it is that we can give it an address and it'll give us back a bunch of numbers. And we can also give it an address and a bunch of numbers, and the next time we give it that address, it'll give us this same bunch of numbers back. In other words, this allows us persistent storage of information. This bunch of numbers is called a sector or a block. In computer jargon, we call such a device a block device for reasons I hope are obvious. Which is great, but not very useful on its own. We don't like to work with data that all comes in 512 byte chunks, nor do we like to reference this data with long meaningless numbers. Block devices are a great computer interface, but we humans usually prefer a more us-friendly way of referencing information. In particular, one common interface is to have the data split into buckets. Each bucket can have any size, from completely empty to very large indeed, and we want the freedom to specify the size with 1 byte granularity. Also, instead of numbers, these buckets are referenced by a name composed of, letters. We call such buckets files. At its most basic form, that's all you need, though there's one more addition that these days is pretty much mandatory. We can sort the files into folders. These folders themselves have names and can reside inside other folders. These folders are called directories. So what we now need is some mechanism that can take the files and directories semantics and store them on an address and blocks semantics block device. The component that does that is called a file system. Again, I'm hoping the reasoning behind the name needs no explanation. I should point out that description of a file system is a little simplified. Almost all file systems have more capabilities than that. Modern file systems usually keep track of the file types, permissions, and ownership, and have algorithms that make sure that an unexpected reset of the computer does not corrupt data. Some don't even have a block device at all. As you'd expect, however, all of those wonderful features make the file system itself more complicated. That's perfectly fine for a file system serving your computer from internal storage, but what about a file system for removable storage, such as an SD card or a USB thumb drive? It turns out that for those, the industry favored simplicity over features. The standard file system for SD cards provides files and directories and very little else. So on review, I realized the choice of words here could be offensive to some people. A better phrasing is, whom yo calling fat? Please accept my apologies. Introducing the File Allocation Table file system, henceforth referred to as FAT. We're going to focus on one specific variant of the file system called FAT32. Originally released in 1996 as a minor revision to Windows 95, and a special revision at that, it was not released in retail, so the only way you could get it at the time is to buy a new computer that was pre-installed with it. That version was called Windows 95 OEM Service Release 2, or Windows OSR 2. The first retail release of FAT32 was only about 2 years later with Windows 98. On a personal note, at the time OSR 2 came around, I was leading a project helping Packard Bell, then US's biggest computers OEM, revise their factory and recovery CD installation so that it, work. So I got my hands on an OSR 2 OPK, that's OEM pre-installation kit, fairly early on. FAT32 was such a huge relief that I spent quite some time in trying to retailize the OPK installation. I was thinking of doing a video about the Windows 95 OPK install process, but it requires a huge amount of time investment. Let me know what you think. It'll definitely be in my other channel if it does come up, so subscribe there as well. There are two main challenges to creating the file hierarchy over a block device. The first and obvious one is naming the files. The solution FAT took is to have a directory with fixed structure. So each directory is stored just like a file. In it, The files are managed in fixed-size records. These records contain the metadata of the file type if applicable, information such as creation and modification dates, permissions, and, crucially, the file's name. FAT, at its core, uses a very strict naming convention. Each file name has 11 bytes, split internally to 8 bytes of base name and 3 bytes of extension. If that's not limiting enough, the bytes are each only a small subset of ASCII, resulting in file names allowing only uppercase Latin letters plus a few extra characters. It should be pointed out that modern FAT file systems allow more choices for what a file name can be composed of, but this is an extension, using whole directory entries just for the extended name. Even with these long file names, each file always also has an uppercase 8 and 3 name, and you can always choose to only address it via that name. The directory entry also has the file's size. This should be fairly obvious. Since the underlying unit is a whole block, we need a way to give the file's actual size with better granularity. This field is stored as a 32-bit value in bytes. One thing you'll notice is that this makes it impossible to create a file that is larger than 4 GB. There's just no room to store a bigger file's size in the directory entry. Having a directory entry with the file's name, size, and attributes is great, but it still misses one tiny, potentially relevant piece of information: the file's actual content. Which means that the directory entry has one last piece of information about the file, the first block where we can find the file's actual data. This solves all of our problems, assuming the file is smaller than 512 bytes. If the file is bigger than 512 bytes, then a single block isn't enough to hold all of the file's data. This means we now need to know where the file's second and then third, fourth, and so on blocks reside. FAT's solution to that is to have a central place on disk where the blocks are linked to each other. Here's how this works. Suppose we have a directory entry for a file and it says the file's first block is at block number 17. We can now read block number 17 and get the first 512 bytes of the file. We can then go to this central table, look up at the 18th slot, because remember we're zero-based, and it will say 258. This means the file's second block is at block number 258. If we go to entry 258, we can read where the file's third block resides, and so on. At some point, the inevitable will happen, and we're going to read the whole file. The last block of the file will have a special value, typically hex FF some amount of Fs 8. That means that this is the last block of the file. This value is called end of chain, or EOC. I said EOC. There is one more use for this table. One thing we did not discuss is block allocation. When we want to create a new file or extend an existing one, we need to find a block that isn't already in use. We can find those because they have a 0 in the corresponding entry in the table. So now we know that a block whose entry is 0 is free. If it contains the EOC mark, it is unconnected onwards, and the other values are the chain where the data in this file continues. There's also a bed block marker, but that's pretty much it. This table is called the File Allocation Table, or FAT, hence the name of the file system. One thing that should be very clear about this scheme is its simplicity. The CompuSAR implementation is admittedly a minimal one. I only support reading only of the 8.3 file names and only allow reading files sequentially start to finish. Still, the entire implementation is only 450 lines of code in C++. The code that formats a directory entry in a textual layout is almost as long as the code that reads in directories plus the code that reads in files. So for comparison's sake, this is all the code that I need in order to print the content of all the files with txt extension in the root of the SD card. This is the code for actually reading the file's content, and this is the next cluster function calculating the chain. It is pretty much as simple as that. And while those limitations may seem very restraining, aside from the read-only part, this is all Compusar is ever really going to need. It's also all the UEFI loader in your BIOS or the loader in your bootloader will ever really need. Sequential and read-only is still very, very useful. The 32 in FAT32 came from the size of the FAT entries. As the name suggests, there are different versions of FAT with smaller entries. In particular, there's FAT16, where each entry is 2 bytes, and FAT12, where each 3 bytes provide 2 entries. FAT12 allows up to 4084 blocks. Assuming each block is 512 bytes, this means it can address a maximal storage media of 2 megabytes. In other words, FAT12 is what we format floppies with. FAT16 allows up to 65,000 blocks. Well, 65,536, 24. Assuming 512 bytes per block, that allows the file system to grow to 32 megabytes. That is not very big. For reference, I got my very first hard disk in 1991. It was a Western Digital Caviar series, and it was 40 megabytes in size. The solution hides behind the fact that I fibbed a little detail here. The entries in the FAT are not, in fact, blocks. Instead, they are clusters. Each file system could cluster multiple blocks into a single allocation unit, thus allowing use of much bigger file systems overall while still using 16-bit for addressing. My 40 megabyte hard disk was on the Amiga, which used a different, better file system, but had it been on a PC, it would likely have been formatted with 2 blocks per cluster, meaning that the minimal allocation size would be 1 kilobyte. So a single byte file would take up 1 kilobyte of disk space. Not great, but it's a reasonable compromise, especially if you consider that FAT itself takes less space this way too. Also remember that there are 2 copies of the FAT, although no one is sure why, as no file system implementation ever reads the second copy. Except that by the time 1995 rolled around, 1 gigabyte disks were not unheard of. To format a 1 gigabyte volume with FAT16 would require cluster sizes of 32 blocks. Each allocation unit would be 16 kilobyte. The pain was felt really hard. Did you ever wonder where the habit of partitioning a disk into 2 drives came from? Well, now you know. So when FAT32 came out and allowed returning to small allocation units, that was a huge deal. Now you know why I kept trying to figure out ways to extract that ability from the OPK. There were multiple implementations of FAT, but for many years these were based on reverse engineering the structure of the file system. That's not a huge problem. It is, after all, a very simple system. In the year 2000, Microsoft wrote an official documentation of the FAT file system. Reading through this provides some illuminating moments. For example, take this question. How can you tell which type of FAT this is, whether it's FAT 12, 16, or 32? One would expect there to be some place that gives a bunch of metadata over the file system where that is written, and one would almost be correct. The very first block of the file system indeed contains a struct called BIOS Parameter Block, or BPB. It has such info as bytes per sector, sectors per cluster, how many copies of the FAT exist, and the total number of sectors on the volume. Of note, it also contains 2 textual fields. One identifies the system that created the file system. Here, for example, we have mkfs.fat, which suggests this SD card was formatted on Linux. The other one, according to the standard, will contain either FAT, FAT12, FAT16, or FAT32. So there you have it, right? Well, no. The standard makes it clear in no uncertain words that this field should not, in fact, be used for that purpose. considering this field is located in different offsets on FAT32 and in older versions, this actually kinda makes sense. But still, this header that contains all of that useful information about the file system does not tell what type of FAT it is. Now, the BPB does have how many sectors each FAT takes, and also what's the total number of sectors on the volume. I'm pretty sure dividing the two numbers bring you very close to the answer, but the standard says no. So in the chapter called FAT Type Determination, you can hear the writer's frustration over this. I'm going to mimic what I'm sure must have been the writer's voice while writing this. There is considerable confusion over exactly how this works, which leads to many off by 1, off by 2, off by 10, and massively off errors. It is really quite simple how this works. The FAT type, one of FAT12, FAT16, or FAT32, is determined by the count of clusters on the volume and nothing else. Then again, I'm guessing this was set up to fail. There's no way people were supposed to figure this out on their own. So here's the algorithm. We calculate the number of clusters in the volume. I'll let the standard do the talking. Please read everything in this section carefully. All the words are important. For example, note that the statement was count of clusters. This is not the same thing as maximum valid cluster number, because the first data cluster is 2, not 0 or 1. Now we can determine the FAT type. Please note carefully or you will commit an off by 1 error. In the following example, when it says less than, it does not mean less or equal. Note also that the numbers are correct. The first number for FAT12 is 4085. The second number for FAT16 is 65,525. These numbers and the less than signs are not wrong. We then compare it to certain predetermined numbers. If it's less than 4085, it's FAT12. If it's less than 65,525, it's FAT16. Otherwise, it's FAT32. If you don't get how the off by 10 could come around, here's what you're missing. Programmers love to go by powers of 2. 2 to the power of 12 is 4096. 2 to the power of 16 is 65,536. FAT12 is used if the number of clusters is smaller than 11 less than 2 to the power of 12, and FAT16 if it's smaller than 11 less than 2 to the power of 16. Why? The standard doesn't say. I believe it's because a few values are reserved for EOC, free, and other indications, so they can't actually be used. In the previous video, I promised to explain why CompuSAR will support SD cards only up to 32 GB in size. I then went ahead and not explained it. In a move that is becoming atypical of this channel, I'll actually do explain it now. As we could see, FAT32 can handle much bigger volume sizes than previous versions, but it, too, has its limitations. While in theory, FAT32 can support volume sizes of up to 128 GB without increasing the cluster sizes, in practice you'd start running into trouble much sooner. In particular, the 4 GB file size limitation is becoming a restricting factor at those sizes. So Microsoft does not recommend creating FAT32 volumes bigger than 32 GB. The SD standard, therefore, dictates that cards up to 32 GB in size should be formatted with FAT32, and bigger cards should be formatted with a related file system, also by Microsoft, called exFAT. If you put a bigger card into a system not supporting it, the block device part will work more or less just fine, but the system will not be able to understand the file system. And yes, you absolutely can format a bigger card with FAT32, and then those systems probably will work with them. But why would you? Think of it like that. The Apple II, throughout the 16 years it was in production, had around 100,000 software titles released for it. Assuming an average of 2 sites per title, I suspect the actual average is actually even lower, and at 140 kilobyte per diskette, This amounts to 26 gigabyte. So you need 26 gigabyte to store every single software title ever released for the Apple II. A project such as CompuSAR simply doesn't need to support bigger storage. Recent times were very hectic for me. A combination of a horrible Heisenbug I still haven't been able to pin down, and some turmoil in my personal life, including spending a whole week in bed sick, caused this video to be published 2 whole months later than scheduled. So I would like to extend a huge thanks to all of the viewers who stuck by me, and especially my loyal Patreon supporters. I really appreciate your patience, and thank you for watching.